fast. It did go by fast. So we're sitting right here. It's going to take today and part of tomorrow to cover this section. Then we'll start 9.3. The project is due on Thursday, so please make sure you're working on that. We did do an example of how to solve a problem like that in class in your notes. So if you would go back and take a look at that, don't come and say, "Hey, I don't get how to do this. You didn't show us how to do that." I realize I didn't show you how to do that particular project, okay, but I did show you how to solve it. With a different type of problem. So that project is due here. We'll have a Q&A day here. Good time to straighten up any issues that we've got with this because we're going to be talking about exponentials and logarithms, something that's huge in Math 1050. We'll go over 9.5 and 9.6. Then we'll hit, we only do one section in Chapter 10. It's on circles. We'll review. We've got an exam a week from Thursday. And then we start with the final review packets. I did hand those out, right? Okay, so please make sure that you're working on those, keeping track of those. I think we put them in order, wrote down which was due when and that sort of thing. And then the final exam is on Thursday, I believe at 9 or 9:30 or something like that. I'll double check that for next time and then we'll go from there. Okay? You will notice something else. Everything from now on is bookwork. You need to have your textbook here. I mentioned this last week. All of this stuff is out of the book. Okay? So please make sure you get used to that. Bring your book. If you want to take, your book to the office and have them copy off just the sections with the numbers, that's fine with me. So you don't have to cart the whole thing around. But you do need to have that, yeah.
So does that mean there's no more Math Excel?
No, it's still available if you want to look on there.
Yeah, no more assignments there.
No more assignments on there. And there are two reasons for that. One, I don't like the way that Math Excel handles, especially logarithms. It's not, in my opinion, it's not in your best interest to learn it that way. I'd much rather have you do it the way I'm going to show you. And also in 1050, you don't have Math Excel in 1050. Okay, so if you want to use Math Excel as a help for this, that's fine. Please don't use it for the logarithms. And I'd really prefer that you come and ask me for help if you need help on something. And in 1050. There is something that we can make available free. I've actually mentioned it on my website before. It's interactmath.com. You can go there for Math Excel-like problems and helps and, help me solve this and view an example and stuff like that. But for now, it's just all out of the textbook. Just mainly, I don't like the way it handles some of the stuff in these chapters, and you need to get used to that for 1050, okay? And for college prep, for that matter. You can turn in your book before the final. If it's not in on that day, then I'll yell at you. And Camille will hunt you down and kill you. But she'll do it in a very nice way.
It'll be a quick.
Yeah, quick and painless stuff. Okay, any questions? Okay, so let's take a look at 9.2. The starter question is something that we've seen before. It's a parabola, a quadratic function. It's already written in vertex form, so that's really nice. And it says label the vertex and 2 other points. So on this particular problem, we know that because we changed the x before we squared to make the shape, we know it's going to move it in the x direction, the opposite of what you'd think. So this is going to move it back 1 unit, so 1 unit to the left. And then this is going to function after the function creates the shape, so we're going to add 8. So it's going to be at 1, 8. So we're going to go over 1 and up 8. So that's going to be about right here. I'll blow this up just a little bit so we've got a little better picture. And then negative 1. Thank you very much. Back 1 and up 8. So we're right there. Is that good? So the vertex is negative 1, 8. Probably would have caught that eventually. So here's our axis of symmetry. It doesn't ask us to label that or anything, but it's a good idea to keep that in mind. And then it says label 2 other points. This negative indicates that the parabola is going to open down, and the 2 indicates that it's been vertically stretched. So the points have been made taller than they used to be, or the graph is steeper, if you want to think of it that way. And that really is the best way to think of it. So we're going to go over 1, and we're going to go down 2. We'll go back 1, and we'll go down 2. That's really enough to draw the shape of the graph. If we were to do another point, remember we'd go forward 2 and then we'd go down twice as far as we normally would. So that would be down 8. So the graph looks something like this. And as long as I've got things labeled, whoops, x equals negative 1 here. As long as I've got things labeled and I indicate that that extends forever in both directions. So this would be 0, 6, whoops, 0, 6 there. And this would be negative 2, 6 for that point right there. If you wanted to label these other ones right there, they're not hard to find. They'd be pretty easy. Okay, well, my point in doing this is if you know the shape that a function makes, it's not very hard to graph a transformation of that shape. So whether we stretch it or shrink it, slide it left, right, up, down, whatever it happens to be, if we're familiar with the shape, graphing a transformation of that shape should be pretty easy. Okay? So again, just as a reminder, every function makes a shape when you graph it. Doesn't matter whether it's a line, a parabola, whatever it happens to be. Okay? We've studied a lot of these linear functions. Okay? And we call it that because it makes a line. And we've studied a lot of these quadratic functions. And the graph of a quadratic, what is that called? What shape? Parabola. Okay? So once we know those shapes, it's pretty easy to change those based on some sort of transformation, a stretch, a shrink, a slide right, left, up, down, that sort of thing. Well, what this section is about is it's about something called an exponential. An exponential is a new type of function and a new type of shape. So what we want to do is we want to explore this a little bit. Okay? This is an exponential. An exponential has a base that's a number, okay? And an exponent that's a variable. Now that base has to be a number that's not equal to 1. And we usually use positive numbers. Okay, we make this pretty easy for the time being. We wouldn't want to use a negative number. Those, I suppose, come up occasionally, but I've got a couple degrees in math, and I haven't worked with very many of those. Okay, so we're talking about a positive number other than 1 that's used as a base. And then the exponent can be any number we want. Okay, so let's think about what we get here with this shape and this function, with this shape and this function, and this shape and that function. Now, you'll notice that each one of these has a 2 and an x. It's just that they're in different places. So what do I get when I plug a 10 into this? So let's figure out what f of 10 is here. It's 20. Just plug in a 10, times it by 2. All this function does is take the number you plug in and times it by 2. It doubles it. Let's figure out what g of 10 is. If I plug a 10 in here, I get 10 squared and I get 100. Well, that's quite a bit bigger, but it's not, it's not ridiculously bigger, okay? What this function does is when you plug a number in, it squares it, or in other words, it multiplies it by itself. Here it always multiplies it by 2. Here it multiplies by itself. Now this one again is different. If I find h of 10 on this problem, that means 2 to the 10th. It means take 2 and multiply it by itself 10 times because we plugged in a 10. If I plugged in 20, it would mean take 2 and multiply it by itself 20 times. Does anybody know off the top of their head what 2 to the 10th is? 1024. Thank you very much. So here are the answers. Plugging in the same number, I get these 3 different answers. I get a 20 when I plug it into this linear function. I get a 100 when I plug it into this quadratic function. And when I plug it into this exponential function, I get 1024. This is a huge number relative to these other 2, okay? So even with the same numbers or variables, if I just put them in different places, they do drastically different things, okay? So our goal here is to figure out what shape do we get out of an exponential. Now, it's generally not very efficient to plug in points and then plot those points. But I do want to do that for this particular first couple of problems because it's going to illustrate the idea of what an exponential does. So the first thing we're going to plug in is we're going to plug in a -1. So I'm going to plug in a -1. So I get 3 to the -1. Then I'm going to plug in 3 to the 0. So I plug in a 0. Then I'm going to plug in a 1 and I get 3 to the 1st. Now, I'm hoping everybody here can quickly figure out what number each one of these represents so that I can graph them. If you can't, we'll do a little bit of review and we'll go backwards here because this is the easiest one to figure out. What is 3 to the 1st power? It is 3. So that point is going to be on the graph. What is 3 to the 0? Any number to the 0 power is 1. So if I plug in a 0, I get out a 1. 3 to the -1. What does the negative in the exponent mean? Okay, it means a word. It doesn't mean flip it, but what's the word? Reciprocal. It means reciprocal. Not inverse, it means reciprocal. Okay, flip it is the idea. The technical name for it is we do the reciprocal. So that literally means 1 over 3 to the first, which is 1/3. Okay? Yeah.
So does that mean on those kind of problems, every like pretty much the y-intercept is always going to be 1?
Yes. On the parent graphs. Very good. Okay? And we'll get there. So let's graph these points right here. Now this is a fraction. It's a bit of a pain, so let's just kind of estimate. If I go to -1, I go up 1/3. That's that point right there. 0, 1, that's right here. 1, 3, that's right here. Now, this is not a line, and it's not a parabola. Take a good look. If I did a line, they'd have to be in this line right here or this line right here. Clearly, this is not a line. This has a curve to it. Okay, and it's not a parabola because normally with a parabola I come down and then I go back up. This one continues going down. Now, for the heck of it, on this particular one, I'm going to plug in a couple other points. Let's plug in a -2 and see what we get out, and let's plug in a +2 and see what we get out. If I plug in a 2, let's do that one first. 3 squared, I get 9. Well, 9 would be, if I counted right, that would be way up here somewhere. And if I plug in a -2, this is going to be 3 to the -2. Again, what does the negative mean? What word? It means reciprocal. Okay? So this literally means 1 over 3 squared, which is 1 over 9. So you can see that as big as these numbers are getting, as fast as these are growing big, these are getting really small. So this would be -2 and 1/9, barely above the x-axis. So here's what the graph looks like. Extends forever in that direction and forever in that direction. Now, if I plugged in a 3, what would I get? 27. It would be huge. It would be way up there. It would be off the, even on your paper, it's probably off the top of the paper. Okay? If I plug in a -3, what do I get? 1/27. So these get smaller and smaller and smaller. But would I ever get a negative answer out of this? No, because I'm taking a positive number and raising it to a power. This is always going to be positive, so this is always going to be above the x-axis. Okay? So this is going to come out here. This is going to have a horizontal asymptote of y equals 0. So I'm going to write HA for horizontal asymptote. Is everybody okay with that? We talked a little bit about asymptotes. You've seen those before? Okay, so let's talk about an asymptote. Okay, that's how you spell it. It's called an asymptote. Okay, it's not asymptote. Okay, doesn't have 2 S's in it, by the way. Okay, so it's called an asymptote. Okay, and it is, for the time being, we'll call it a line that approximates the graph. So what we mean by that is out on this side, it gets really close to y equals 0. It gets really close to the x-axis, but it never actually touches the x-axis in this particular case. It just comes out here and levels off, gets flatter and flatter and flatter and flatter the further out we go. Okay? Now it said graph it and label 3 points. These 3 points are -1, 1/3. This is 0, 1, and this is 1, 3. Any questions there? Okay. Now, let's take a look at these next 2. Again, I'm going to pick an x and figure out what the y is. I'm going to plug in these 3 points, -1, 0, and 1. And I'm going to figure out the y's are that go with them. So this is going to be 2 to the -1. What is it? It is 1/2, because that means reciprocal. So that would be 1 over 2 to the first. 2 to the 0. Parker, what is it? It's always going to be 1 on these parent type functions, and if I plug in a 1, I get 2 to the first, which is 2. So let's label those points. -1, 1/2, 0, 1, and 1, 2. Now again, this has a horizontal asymptote. It's the x-axis, it's y equals 0. And then it comes over here and it bends upward and looks like that. So its horizontal asymptote is y equals 0. It continues to get bigger and bigger and bigger, and these 3 points again are -1, 1/2, 0, 1, and this point is 1, 2. Any questions? Sure? John?
I'm just wondering, so when it has a positive thing that, x, any of that would have 0, 1 as its 100%.
Yeah, because whenever you plug in a 0, you're going to get a 1. So let's take advantage of that right now. So here's x, here's y. If I plug in a 0, do I even have to look at this mess over here? Not if it's a parent function, not if it's a positive number raised to an exponent that's a variable. Okay? If that's the case, when I plug in a 0, I'm going to get a number raised to the 0, so I'm going to end up with a 1. Everybody okay with that? Okay, what do I get when I plug in a 1? I get the number, I get the base. Okay? And if I plug in a -1, I get what? I get the reciprocal of the base. So that is 2. So let's take a good look at this. -1, 2, 0, 1, and 1, 1/2. So this one doesn't start down and go up. This one starts up and goes down like this. And again, here are the points. -1, 2, 0, 1, 1, 1/2. And again, it's got a horizontal asymptote of y equals 0, only it looks like this on the right end, not on the left end this time. Okay, any questions?
Oh, just a quick question.
Yeah.
So, like, on our homework, are we supposed to label the horizontal asymptote as well?
It'll tell you. Okay, we'll do enough examples. You'll see what I want you to do. Okay, any questions? Okay, so it said graph the following exponential functions, label the 3 points, and name the functions. Okay, now we didn't name this one up here, but every single exponential has a name. They're all exponentials, but we name them according to the base. So this is called exponential base 3. That's the name of that function. What's the name of this one? Okay, so exponential base 2. That's what we call that. And this would be exponential base 1/2. Now, I would like you to, for the time being, every time you graph an exponential, write the name for the first several, but from now on, I need you to think of the name. These have names and they are very significant, and they're very significant once we start doing their inverses. It would be like not having a name for the squaring function and then just saying, well, we square that, we're going to call the inverse of that the blob or something like that. Okay? It makes a lot of sense to say I'm squaring something and the inverse is the square root. See how they've both got that name in it? So those names are important. They help us understand the inverse of those functions. So now let's talk about a general exponential function. You can call this like the parent function. Just like when we were graphing quadratics, we said, well, hey, let's figure out what y equals x squared looks like. Let's figure out that basic shape, and then let's know what to do with it. Okay, now the cool part is I've already heard some people answering some of these questions. You'll notice that here, whenever you plug in a 0, what do you always get regardless of what the base is? You always get a 1. Whenever you plug in a 1, what do you get? You get the base, so you get A. Whenever you plug in a -1, you always get the reciprocal of the base. And why do we get the reciprocal of the base? Because that negative is going to go in the exponent, and it literally means reciprocal. So this would be 1 over A. So here are the 3 key points. On exponential base A, this is what we would call this. We would call this exponential base A. Now this is why these are the key points that I want you to graph here. And be thankful that there's only 3, unlike the 5 that we did for a parabola. This is where the bend happens. This is a pretty straight line out here. It's a curve, but it's pretty straight. This is a pretty steep curve. It's still a curve, but it just continues to grow faster and faster and faster. It's just really steep. The bend happens around these points right here, okay? And you can really see it on something like this. Look how steep that is. It looks like it's pretty much going straight up there. Look how flat this is. It kind of looks like it's just going straight out along the x-axis. Those 3 points are where the bend happens. That's why they're important. So a couple other things that we want to keep track of. The base has to be a positive number other than 1. It's not that you couldn't do this. Everybody watch, please. Y equals 1 to the x. Why would that not be very interesting? What would you always get out, no matter what number you plugged in? You get out a 1. So it's not really an exponential. It doesn't grow or shrink. It's not a curve. It's just a flat line. That's why it doesn't technically qualify as an exponential. Okay? Exponential growth. Oops, let me change colors here. This is called exponential growth if a is greater than 1. So this is what we're talking about right here. If I have a 1.5, a 2, a 3, a 9.8, that's going to be exponential growth. It's going to grow, it's going to increase from left to right. If I have a number that's a fraction between 0 and 1, like this one right here, we call this exponential decay. That's what we've got in this scenario right here. Starts big and then gets small. Now let's talk domain and range. The cool thing about exponential functions is you can plug in anything you want. The domain is from negative infinity to infinity. The range, however, like we saw in these examples up here, you don't get out anything you want because the base is a positive and you're always raising it to a number. It's always a positive times some fraction of a positive or a whole positive. It's always going to be positive. So its range is going to be from 0 to infinity. It's always going to be above the x-axis, in other words. Okay? And what type of horizontal asymptote does it have? Y equals 0. Okay? Now, this is for the parent function. We're going to flip this over in just a second and we're going to do something a little bit different. But for the time being, we want to graph each one of these. So, what's the name of this function right here? Exponential base 4. Is this going to grow, get big, or is it going to decay, get small? It's going to grow. Okay? What's this one called? Exponential base 1/3. Is it going to grow or decay? Is it going to increase or decrease? It's going to decay. So let's graph these. So I'm going to do this one in red. Okay, watch please. I'm going to put these points up here, and this is literally how easy it is. Everybody watch. Eyes up here. Well, where'd those go? Gonna have to make it bigger. -1, 0, and 1. Which of these 3 points can I plug in right now? 1. This is going to be a 4 when I plug in a 1. This is going to be a 1/4. Remember, negative, reciprocal of the base. 0 is a 1 no matter what the base is. And if you plug in a 1, you get the base. So let's plot the points. -1, 1/4. 0, 1. 1, 4. And it looks like this. It does say, without using an XY table, we didn't use an XY table, did we? We just wrote down the 3 points just real quickly because we knew what they'd be. Label the 3 points and the horizontal asymptote. Now the horizontal asymptote, I'm going to put it out here. Y equals 0 is our horizontal asymptote. Good there? And name the function. What is this called? Exponential base 4. Okay, let's do the next one. Any questions there? Okay. Let's figure out what these points are. -1, 0, and 1. I can fill one of them in immediately. It's this guy right here. When I plug in a negative, what do I do with the base? Reciprocal. What's the reciprocal of 1/3? 3. When I plug in a 1, I just write down the base, so this is 1/3. Okay, now am I going too fast? Does everybody get this? Any questions? Okay, so -1, 3, 0, 1, 1, 1/3. We'll sketch the graph. It looks something like this. Horizontal asymptote of y equals 0. Out on the right end, out on the positive side of the x-axis. Okay, and I'm just going to draw these lines here for right now just to save some time. Okay, did I forget anything here? It's called exponential base 1/3. Exponential base 1/3. By saying that, we're acknowledging that it is an exponential. We know what the base is. The base is 1/3. And if I know the base is 1/3, I know for a fact